more cases to this project. And the way we're going to add cases is by adding drains, because we want to speed the consolidation and see if that helps us reduce the settlement after the structure is built. So in other words, if we can get a lot of settlement to take place before the structure is built, then when we put on our structure, there's going to be less left for the structure to do. So we're going to do the calculations. I'll show you how. So we're going to consider site 1, and at site 1, now this is the building footprint, and so this is in plan view, the building footprint, and we're going to put, these are all the drains here. We're going to have 144 drains for site 1. If we put down 144 drains, then the spacing is 4.17 feet. And now, if you remember how drains work, if this is our ground surface here, and I have drains in a clay layer, for instance, well, what happens? These drains, water flows into the drain horizontally. And for instance, a particle here could go to this drain, or it could go to the other drain. And so in this region here, we have double drainage. Why? Because the water could go to the right or it could go to the left. So this is a case where our HDR is not going to be dependent on the thickness, the vertical thickness of the clay layer or silt layer. It's going to be dependent on the spacing of the drain. So remember what HDR stands for. HDR stands for the smallest distance, the largest distance that a particle of water has to move to be able to get into a drain. And in this particular case, you can see that it would be half the distance between the drains, because the largest distance would be a particle of water here, and it would have to go either that distance or that distance. So it's going to be, for this particular case, it would be what? My HDR would be the divided by 2, it would be the spacing divided by 2. So what you're going to do is you're going to use the HDR based on the spacing divided by 2. So there's my HDR for site 1, so I'm giving that to you. For site 2, what we're going to do is we're going to space them out at 16.67 feet, and that means our HDR would be half of that, which is 8.33 feet. You can see how many drains I have here. 1, 2, 3, 4. Times 4, I have 16 drains. Here I've got 12 on a side, so 12 times 12 is 144, so I've got 144 drains. So that's the way the drains were selected. And if you look how deep we have to put these drains, so at site 1, what do I have to do? I have to put the drains all the way to the bottom of the clay. So they go all the way through the silt, all the way through the sand, to the bottom of the clay. So that gives you the length of each drain. Is that distance right there. We're going to be concerned about the length of each drain a little bit later. But for now, we want the distance between drains. For site 2, the drains just go down to the bedrock. So we're going to create 4 new cases, 17, 18, 19, and 20. And we're going to have 2 cases at site 1 and 2 cases at site 2. And we're going to, like I say, we're going to have this spacing with an HDR of that. We're just going to use the 12 feet of gravel. And we're just going to have 5 years then the structure with no basement or a 10-foot basement. So we're reducing the number of cases here. And then at site 2, same thing, we're going to have 12 feet of gravel and 5 years. Only then the structure, again, no basement in the structure, 10-foot basement. Of course, we only want to do 5 years because the purpose of the wick drains is to speed up consolidation. So we don't want to do 20 years. We wouldn't gain anything if we did 20 years. So I'm going to do case 17 for you, so we don't really even have 4 cases to do. And so case 17 is site 1. We have 12 feet of gravel. The time is 5 years before the structure, and there's no basement. So that means our Q again is still 1600 PSF. And we have our HDR of 2.08 that we've already come up with. Now, that means what? That means that our capital T is what? C sub V times T over, now it's 2.08 squared. So that gives me, our capital T is 1.12 T. Our elevation at point of interest is negative 19 because that's in the silt. We have to do both the silt and the clay. Gives us our Z, which is the 19 plus 12 is 31. And our Z over B, 0.62. So, and then our times are going to be what? 0 minus, 0 plus, 5 minus, 5 plus, 20. That's for T1. We're putting the structure, we're putting the structure on at 5 years, so we're going to have 0 minus, 0 plus, and then that would be 20. So we can figure out our capital T for both cases. At 0, it's 0 plus. At 5, it ends up to be 5.6, so it's a pretty big number. And it's 28 at 25. So we have big T's. Again, it's 0 here, it's 0 minus 0 plus. And this ends up to be 22.4 because that's 20. So that means what? That means we're way off the chart pretty much. So if you remember the chart, these big numbers just give us 0 excess pore pressure. So in this particular case, we have for these T's, we're going to end up with U excess of zeros. And for this, we're also going to have 0. So, let's see, maybe I can... Where is it? You can see it because what? There's our T is 1.2. So our bigger T's are going to be, they're going to be way in here like that. Because 1.2 is the biggest T we have on this chart. So this is giving us all pretty much zeros for our excess pore pressure. So, oops, this is case 20. Case 21. So, hold on a sec. No, I wanted case 17. There we go. Okay, so we have so those are 0, those are 0. at RT equals 0 plus, I have what? I've got the 12 feet of fill. And then here at RT equals 0 plus, we have our pressure bulb, and the pressure bulb factor ends up to be 0.58 times our 1600, and that gives us this UXS2 of 928. You can all get the U water table. Adding those three pore pressures together, we get these U's. The sigma V, you know, we've calculated that already, and those don't change. So, you know, we can get our sigma V primes. So, you know how that is, and this has got to be the same. And that minus that gives me that. Once I have that, it goes down here. I already have my U's, so I add these two together to give me this. And this goes down to there. Subtract the pore pressure, that gives us this. So we get all our sigma V primes at the various times. And, you know, you've... Okay, so let's do the clay. Now what? Now, again, we have our HDR still is 2.08, but now our C sub V is only 0.82, so that gives me a capital T of 0.19 T, and that changes these so that now I have, this is 0.95, this is big, so I don't have to worry about the big ones, but this 0.95, I have to use the table. So it's double drainage, so I come in here and I'm looking for 0.95, which is in here approximately, and then I come down here and read off, you know, something that looks like 0.1, 2 or 0.13, something like that. And I use 0.11. And the UXS1 is what? It's the 1392, because it's still the 12 times 116 due to the fill. So I get 0.11 times 1392, it gives me 153. And then UXS2 is for the building. I get a footprint or pressure bulb factor of 0.3 times, again, the structure is 1600 times 0.3 gives me 480 for that one. Again, we have that, the water table, that's fine. I add up the water table and the two UXS's. I get those. The sigma V's, we've done these already, so you can get those. And these two are the same. And then this minus this gives me this. I go to here, those two are the same. I add these two, gives me that. And again, this is the same. Minus that gives me this. So I have, again, all of my effective stresses. And again, I have to figure out my sigma prime P. Use the original one. We've calculated these already, 1221 in the silt, 2453 in the clay. We compare it to our sigma V prime I, 2613, 3576. And I take the bigger one, and in both cases, the bigger one is the sigma v prime I. So my 2613 goes here, 3576 goes there, and my sigma v prime F is the 3541 goes here, 4209 goes there, and then we put those into our equations. We've already done this. Again, we're just doing the last portion of the curve, second portion of the curve. I get a delta H. I get a settlement of 1.02 feet, which does not pass. No matter, and this is what we've learned here. And that particular one doesn't work. Case 20. I'm not going to go through it. I think you can go through this one yourself. Similar. Case 20 is what? It's site 2. The wick drains spaced at 16.67, which is an HDR of 8.33. So that gives me our C sub V is 15. 15T over 8.33 squared gives us 0.216 T. And you can take a look at this. I think I don't need to go through every step. In this particular case, what happens is we get a delta H total of 0.494, which does pass. So you just need, since I've shown you how to do these two, I've done 17. You don't have to do it. I've done 20. You don't have to do it. You really only have to do 18 and 19. Now, you need to summarize, of course, all these cases, whether they work or not, and so you need to fill out a table, this table again, and include the latest cases, whether it passes or fails. Okay. So include these latest cases and all that. Now, the next thing that we're going to do is we're going to put some costs on it. And so for each case that works, we're not interested in the cases that don't work, because if they don't work, there's no sense in putting a cost on it. So we just look for the cases that pass, and we're going to put these costs. The fill is going, for the sand, is going to cost $1.20 per cubic foot. The gravel is $1.05 per cubic foot. And where does that fill go? Well, we're just going to say that it's 12 feet of fill, and it's just going to cover the building footprint, which is 50 squared. So you get the volume from that. To remove fill, it's going to cost $10 per cubic foot. Then, if there's a basement, the soil removal in the basement is more expensive. It's $25 per cubic foot. And we're going to use 10 feet for a 10-foot basement times 50 squared, the footprint. Then if we're putting in a basement, we have to put in a retaining wall. And how are we going to figure that out? It's 5,000 square feet of visible wall facing. So when you're standing in the middle of the excavation, you're looking at the wall. So for a 10-foot basement, we're going to use 4 by 50 by 10, which gives us 2,000 square feet of visible wall facing. If we're going to do any dewatering, we're going to look at $250,000 per foot of lowering the water table. And then when we have drains, we're going to look at $150 per lineal foot. What does that mean? So site 1 has 144 drains, and each drain is 46 feet. So it's $144 4 times 46 feet. That gives us the number of lineal feet. And then we multiply by $150 per lineal foot. Site 2 has 16 drains times 50 feet, so you get the lineal foot for that. We're going to consider a delay cost. So what does that mean? In other words, if we put up our building at 5 years, we get more use of the building than if we put it up at 20 years. We get 15 years more. So there could be a 15-year delay. That costs the builder some money because he's not getting any rent from his building. And so we're going to say that the delay is going to cost $733,000 per year. So 15 times 733,000 per year, that's going to give you how much that delay will cost. So the 15-year comes out to be $11 million. If you do just a 10-year delay, which we're going to talk about later, is $7 million plus dollars. So we're going to you want to put costs on this by filling out this table. So here's an example for case 12. First, it passed. Now, case 1, it didn't pass. So don't do it. Skip it. There's no reason to do case 1. But case 12 did pass. So we look at how much the fill costs. What was it? 1.05. So that was the gravel. And so the gravel times 12 times 50 squared, it's that much for the fill. And then we're looking at the basement cost. We have to consider both issues with the basement, which is removing the fill, 25 times 25,000, and then the wall, the retaining wall, and that's 2,000 times 50,000, or 200 times 50,000. These numbers come from here. Okay, so 2,000 square feet is what we're looking at, times, well, maybe I didn't, 5,000, not 50,000, 5,000. To check that number, let's see. Yeah, I must have, I don't know if I made a mistake. I have to look at it. But in any event, there are no drains there. The delay cost, because there's a delay of 15 years, $11 million. There's the cost of this. It's $21 million. So you need to do, all of these, figure out the cost, and we want to figure out the lowest cost. And then at the end, you're going to come up with your own cases, case 21 and 22. Now, you make them up. They have to work. In other words, they have to pass the settlement criterion, and they need to be cheaper than any of the other cases. So our goal is now you've learned something about what works and doesn't work. So I want you to look at your data, look at your results, and use your gut feeling. This is where you learn something, and then you have to see what works, what doesn't work, and come up with an answer that is better than, I gave you a bunch of cases, but there's a better one out there. I'm going to tell you that. So you need to find, and sometimes I say there's a little competition to who can get the cheapest one. But you have to make up your own 2 cases. And so you're going to fill out this table where you choose your own basement, your own maximum fill thickness. In other words, don't stick with what we had. The basement can be 0 to 14 feet. I'm not limiting you to 10 feet. The fill thickness can be 12 to 14 feet. The time at which the structure is built is between 5 and 20 years, not just 5 and 20 years. So you have a delay of 0 to 15 years. You pick your own drain spacing, which gives you your number of drains. So so you create this, you create these two cases. Now, there's some cost logic here that you should use. In other words, what's expensive and what's cheap. What's expensive is the delay. Okay, the delay is expensive, so you think twice before you put on too much of a delay. The basement's pretty expensive, so the depth of the basement, you want to get away with as little basement as you can that still works. It's got to work though. What's cheap is the fill. Okay, the drains are also cheap, so you can increase, the fill maybe 14 feet for 5 years, then remove 2 feet at 5 years. You can do things like that. You must have 12 feet when the structure is built, so you can put on 14 feet, but you got to remove 2 feet. Now, we're at site 2, so we're only doing, so if I didn't say this, use only site 2, okay, with a gravel fill. So we're keeping the number of options down here. So we're only doing site 2 with a gravel fill. And we can increase the number of drains to get faster consolidation, but the closest they can be is 6 feet apart. So we're not going to make them closer than 6 feet. And so this is an example of a case that doesn't follow any of the rules. Now you're going to have to do your own case. This doesn't count as case 21, so you can't use this one. This is not your case 21. But this one is just chosen, based on some logic. 7-foot basement, 14-foot fill. 6 years we're going to build the structure, so it's only a delay of a year. We're going to have a drain spacing of 12.5, and then that gives us 25 drains. So then what do? I do the calculation here. And I'm not going to go through it all. You can do this one yourself. But you can look at this, study this and imitate it. And then I'm going to let you do the calculation of the settlement for this. If it works, if it passes, you should get a cost. But you can't use this one. This is just an example. Do not use this case. But use this information that you learn from this sort of thing to create your own cases. Fill out this. This is case 21. Case 22, you fill out the same thing. And this is case 22. Like I say, and then you're going to do your costs for cases 21 and 22.